So I made a last minute change about how I'm going to address the topic for today. I'm going to start by telling you a story. Hopefully, that the story will have a lesson and you might find it amusing and perhaps wake up. And I'm going to end by telling you even a better story. And between the beginning and the end, it will be all full of stories, except for a small piece where I would like you to pay attention because I do want to take you behind the scenes to show you each aspect of solving real world decision problems. As you know, every business, big or small, has to make decisions. Some of these decisions have to be made in real time, some impact today and tomorrow, and other decisions might impact a much longer period of time. So let us start, as I said, by telling a story, and the story is about a priest and a truck driver, or sorry, a bus driver in Bangalore. They happen to die at the same time, and both of them reached the gates of heaven. So the God looks at the priest and says, well, I like what you have done, and assigns him a run of the house room in heaven. The driver, he was apparently drunk, could hardly walk, and was about to fall. And God assigned him to the palace, the presidential suite in heaven. So obviously, the priest was very disturbed. He said to God, I have been preaching your gospel all my life. And this man that you are giving the palace or the presidential room to has been a drunk, abused drugs, has been mean to people, has never ever done anything that to be proud of. So God looks at the situation and says, unfortunately, it is all about results. When you were preaching the gospel, most people were yawning, as some of you might be, and they were falling asleep. Nobody was remembering me. But when this bus driver, half drunk, was driving on the roads of Bangalore, everybody on that bus was folding their hand and remembering me. God saved my life. So indeed, it is all about results. And when it comes to solving very difficult business problems, business decision problems, it is about the results. Business people do not care whether you use machine learning or deep learning, whether you use operations research techniques or optimization techniques, or what you have. You have to produce results. That is important. So I will go back to my favorite scientist. What happened? There you go. Once he was asked, yeah, okay, all right. Once he was asked, if you were given an hour to solve a problem, how will you go about it? And he said, I would spend 55 minutes defining the problem and only 5 minutes in solving it. And that is so true when it comes to business problems, how we need to solve them. We really need to spend a lot of time in obtaining the right model before we attempt to solve that model. Now, that part of Einstein we do agree with. However, Einstein also said that God does not play dice with the universe, unfortunately. That part is not true. Every business that operates in an uncertain environment, and you are almost sure that whatever you predict will not happen. And dealing with that uncertainty and making sure that you are making decisions that are not only going to optimize what you want to optimize, but will also cope with the uncertain nature of the demand in the marketplace becomes one of the key factors to be folded into solving these business problems. Now, the challenge really is to create the right model. And if you do not create the right model and you pretend that your predictions will come true, or you pretend that you are operating in a certain environment, it can be very dangerous. It can not only leave a lot of money on the table, in fact, it can lead you to a situation which is highly suboptimal. Remember that in the beginning we said it is all about results. And in order to get the right results in the business environment, we have to optimize whatever we are optimizing, but we have to make sure that we account for the uncertain nature of the demand and the marketplace. So, in the beginning, I told you a story, time for the next story, and this story may be true. Prashant, do you remember when I asked you to light a bulb, a 1,000-watt bulb in one corner of the room, and I gave him the task of predicting the temperature here? And Prashant said to me, that's easy. He didn't follow Einstein's style, he didn't think much, he didn't think about modeling. He says, very easy. What? I just need to know the position and velocity of the molecules in the room. I'll write those equations I learned before, and those equations will decide how these molecules collide, and collisions I know produce heat, and I will do all that, and very soon I would have solved the problem. Aha, great. So he bought all the compute power he needed, took all this humongous amount of data, and while the machine was churning, somebody opened the door and walked in. And Prashant says, hey, you didn't tell me that somebody was going to open the door. All my calculations, you have to recompute. And please, before I recompute, I want you to look at what might happen between now and the time I solve the problem. You know, it's a difficult problem. I need a lot of compute power so that I can account for it. Otherwise, I would have wasted my time. Oh, good. So I called Prashant. I said, Prashant, it's not up to you. Let me see if I can get help from someone else. And another person comes and says, oh, I don't need any computers. I just need an envelope. I'll model the problem that the temperature varies as inversely as the square of the distance from the source. And I can now forecast the impact of lighting that bulb here very, very easily. The real world problem remains the same, but there was one way of modeling the real world which resulted in a solution that was very fragile. It couldn't cope with any disturbance. Used a lot of data, and somehow people believe that the more the merrier, but is that really true? I love big data, but I love relevant data even more. I love complexity, but I love making things as simple as possible, but not simpler, more. And guess who said that? You should try to make everything as simple as possible, but not simpler. Einstein. I have a lot of respect for that man. So, moving on, all of you, I'm pretty certain, are familiar with the Tower of Hanoi. So before I go there, I want to ask everybody here, I'm told it's an Indian story, a king who invented the chessboard. He said, place 1 grain of salt or 1 grain of rice on the first one, 2 grains on the other one, and fill my chessboard. Because he was very happy that this man had invented the game of chess and the king enjoyed playing it. So the king says, you can ask for my daughter's hand in marriage, I'll give you half the kingdom. What the hell do you want this nonsense for? Just some amount of rice. Actually, it turns out that the amount of rice to fill that chessboard will exceed the production of rice if the entire Earth's surface was a rice paddy. Tower of Hanoi, you have to, it is said, the fable says that God had 64 discs placed. These are golden discs on a rod of diamond, I guess. And the job of the priest is to transfer those from one of those towers to another tower. And the constraint is that you cannot place a larger disc on a smaller one. So if you figure out the strategy, you will soon realize that it would take one move to move the first disc, 2 moves for the next one, 4 for the next one, and so on. So how long, let's say the priest is very fast and he can do a move every second. How long would it take him to complete this task? Any guesses? Well, how many billion years? It will take, if I calculated correctly, I think 58,000 billion years. And 58,000 billion years. And according to other sources, people who have tried to measure expectation of how long the universe will last, it's approximately 20,000 billion years. They came very close. I don't know about the story, but there are certain problems which have this problem that in order to solve them, as the size of the problem increases, it starts to take exponential amount of time. Your traveling salesman problem, as you all know, is NP complete. Okay? And the complexity theory paradigm tells us that the general problem solving paradigm is not going to be effective in solving problems that are NP hard and so on. So how can one deal with this intractability? In a practical word, if a traveling salesman has to start from a city, visit each city once and come back to where he started from, and you want to do that by minimizing the total distance traveled, that really is not a real world problem, because what you might be interested in is minimizing the overall time it takes for him to service, go through that route. In any case, if you had to solve this problem, you know that if the number of cities is too large, the general method of solving this problem is not going to work. Traveling salesman problem is NP hard or NP complete, I forget what. In any case, you might want to figure out that you want to divide these cities into clusters, small enough that you can efficiently solve the traveling salesman problem within those clusters. Once you have gotten that, then you consider those clusters as nodes and see how you can minimize the distance. And in the real world, whenever you have to do it, you are really going to find out the trunk routes of how to go from here to there and separately solve the problem of how to go to that trunk point from various places. So the real world usually has a structure. And the general problem solving paradigm throws away that structure and does not take advantage of it. So if you can find a way where you can try to simplify the problem by exploiting the structure of the real world and simplify it to a point where you can actually be able to solve it in real time and be able to cope with the uncertain nature of the demand in the marketplace, then that is what may lead you to a solution to a practical problem in a meaningful manner. And remember, a slightly suboptimal solution found in time may be much better than an optimal solution too late. We are dealing with the business world, and therefore we have to be very practical in how we approach these problems. So, everything has to do, well, I have never given a talk in India, so I chose my favorite example because I'm aware of an individual that went from India. He was from a village. His dad used to have a, a farm where he kept cows and sold milk. And this guy went to Cornell, I think he went to Carnegie Mellon, I was there, yeah. So he went to Cornell and got his education in operations research, nonlinear, linear programming, integer programming. He even learned machine learning, deep learning, all of that. And then he came back to his village and he looked at what his father was feeding the cows and said, this is very expensive. Have you ever tried to optimize? Okay, the father was reluctant to allow him to, but said, well, perhaps all this education is not a waste. Let's see what he will do. So this man, this young kid, went and said, here are all the foods that are available for the cow. And for each item, what are the minerals and vitamins, per kilogram? And then he set up an optimization problem of, say, X1 of food 1, X2 of food 2, the rest, minimize the total cost subject to the constraint. And the constraints were that all the mineral and vitamin needs of the cow are satisfied. He found that the solution would cost 1/3 of what his father was spending in feeding the cow. He was very thrilled and went to his dad and said, Dad, I'm not only going to save you a lot of money, I'm going to increase the milk production. It might even double. Why? Because all the mineral and vitamin needs of the cow will now be met. I have done this study and I have this optimization done. So father reluctantly agreed because he believed that the best way to teach someone a lesson is to let them learn from their own experience. My father did that to me, and I'm sure that I'm doing it to my children as well. Yeah, experiences. There's no substitute to experience. Well, that reminds me of another story. There is, sometimes, remember, Einstein said, imagination is more powerful than experience because your experience is limited to what you know and what you understand, whereas imagination has no such limits. Imagination includes what you do not know today but may know tomorrow. It also includes things that have not been a part of your experience and can become a part of your experience later. But then I'm going on a tangent. The real thing was that instead of increasing the milk production, the cow started to look very sad, and gradually the milk production actually dropped to a point where the cow stopped giving milk. How could that have happened? The cow did not like the taste of the food. And my friends, mathematical optimality is very different from business optimality. Now, we do work with the hotels and airlines, and we provide them with pricing solutions. So we can solve a very complex NP-complete problem by using tricks of the trade, by making sure that we don't assume we know all. We know that it is uncertain. We also know that we can model things differently. Things that are important will be modeled in a lot more detail, and things that are not so important may be modeled in a very cursed way or ignored totally. And doing all that, if we produce a price, well, what happens if the customer does not perceive that to be fair? Or if he feels that the airline or the hotel is gouging them? All your mathematical optimality may go down the drain, and you may find yourself in deep, deep trouble. So yes, mathematical optimality is important, but when you are really solving a real world problem, there are things that you have to take into account which people may be ignoring, and that should not or could be ignored. So essentially then, so far what we have said is that there is a real world out there and we really want to control that real world or make choices and decisions regarding that real world. We have to capture that real world through some kind of an abstraction. Now, once we have a model of the real world, we can apply any technique to solve the problem, and we use the output of our optimization to control the real world. So it becomes a legitimate question to ask. If I find that it takes me forever to solve the model, or if I find that it is too complex, could it be, just could it be, that this complexity belongs not in the real world, but in the way I have chosen to model the real world? Let me give you an example. Remember we talked about the traveling salesman problem? And we said what? That a general traveling salesman problem cannot be solved. If I give you 1 billion cities, how many of you think you will be able to produce an answer that is optimal for me by tomorrow morning? You can use all computers you have, I don't care. Nobody. But if the cities were around a lake, an idiot like me can solve the problem in no time. Just go around the lake. Now you take a problem where the cities are around a lake and you feed it to the general purpose technique of solving the problem will still be intractable. You will not be able to solve it, whereas somebody who notices that structure and can exploit that structure would have produced the answer in no time. So my contention is that when you are dealing with a real world, if you look hard enough, you will find structures that you can use to simplify the problem, and you should be able to make things tractable and solve them to their optimality. The difficulties associated with the real world are, if you look at how, let's take the example of airlines. An airline has planes of different sizes. They have to publish a schedule and they have to assign capacity to the routes. Okay? I'm going to this flight which goes from this city to that city, connects so on and so forth, the hub, that these are the planes, size of the plane that I'll put on that route. There is a separate department other than the capacity planning department that has to price each of these flights. Now imagine that these people are going to solve the problem that they are solving in their own silo. So the capacity planning guy looks out the window, perhaps he has a telescope, I don't know, but he sees this flight always goes full. He sees this flight always goes full. With or without a system, what do you think his thought is? Next time, if I get a chance, when I get a chance to replan capacity, I'm going to do what? Put a larger plane on that route. Unfortunately, the pricing guy is also looking at the same flight and sees this flight is always going full. So he says, once I get a chance to optimize, what am I going to do? Re-optimize, I'm going to increase the fares. Both of them have solved the problem in their silo to optimality, and in fact their decisions are right. Unfortunately for the airline though, they are now landing up in a situation where they are increasing capacity on a flight where prices are being raised. Now does that make sense to anyone? What went wrong? And that is what goes wrong when we try to solve the problem by dividing it into solvable pieces, and we decompose that problem. Now, decomposing a problem into solvable pieces and optimizing in silos can be very dangerous to the health of the organization. Yet, the overall problem, solving it, is not possible because of the computational complexity, and especially when the problems that we are solving sometimes may need solutions in real time. So, what choices do we have? What can be done? Well, every time you take a problem and you break it into sub-problems, you increase the total amount of work because the sum of those pieces will not add to the complexity of the original problem. There is some decomposition penalty that you pay. So clearly, when you do this, you have to do it in a way that you minimize that decomposition penalty. Also now, once you are able to solve these problems in their own silo, you know that you are not going to be able to reach global optimality for the overall solution. So what you have to do is find a technique that allows you to partition the problem in a manner and solve it in a manner that global optimality is preserved. Which means that perhaps what I can do is, once I solve those problems in their own silos, I use the current solution to do something different and re-optimize, and I have to do it in a manner that when I converge, I would have converged to, if I could solve the total problem, whatever the optimal answer was, I'm able to achieve it. There lies the science, the art of solving these very difficult problems. So, yes, we need global solutions, and yes, if we partition those problems and only optimize in silos, we are not going to be able to reach the global optimality. Therefore, we have to learn from solving these sub-problems to partition the problem again in a manner that allows me to preserve global optimality. Now, for all business decision problems, we need ways to solve them, quote unquote, optimally, and these are of great, great value. And we have one part of it discussed so far, that is dealing with the complexity. Let us not forget that there is another part that says we also cannot and should not assume that we can predict, because we know whatever you predict is not going to happen. Think of forecasting for a minute. And my claim is that people, including academicians as well as vendors who work in this area, are not really getting to the crux of the matter. And the crux of the matter is this: how do we measure forecast accuracy? Every time I have looked into it, people talk about, after the fact, what was the forecast? You may use any method you want, including AI techniques, neural networks for forecasting, machine learning, I don't care. Ultimately, to judge the accuracy of your forecast, what people are using is what happened after the fact compared to what they forecasted to happen, and that difference, some square of that or some function of that, is a measure. Now, I can give you a forecasting problem where your job, I'm going to throw 100 coins, and I want you to forecast the number of heads. The correct answer is 50. There is no error. However, when you do toss those 100 coins, sometimes 40, sometimes 60. But according to my measure of forecast error, I would see that no different from before. But the real world consists of both. It has patterns, it has intrinsic volatility. So how will I tell? Well, if the error is due to a pattern that I am missing, looking at the problem more carefully and working harder will create a better answer. On the other hand, if this is intrinsic volatility, I'll be wasting my time. I can spend infinite time trying to improve my forecasting accuracy, but it has got nothing to do with it. It's the natural volatility. And if the forecasting measure itself cannot distinguish between the two, how? Well, there is an easy answer. The answer is it is never enough to forecast a number. We also need to forecast the uncertainty around it. And for those of you who are not done a lot of forecasting, you can think of real data consisting of patterns and some noise added to it. So try to think about it as excluding, removing these patterns from it by some means. So these patterns, apparently, you are going to say, rely on them repeating, and therefore you will use the pattern to produce a point forecast. Hey, after you removed all the patterns, this garbage that was left, which is pure noise, and there are mathematical ways that you can tell this is pure noise by looking at its Fourier transform and seeing the energy spread all over. So what do you do to this point forecast? You need to say, this is prediction, and scientists don't believe in predicting. To convert that prediction into a forecast, I need to take that noise and add it here and say, all I can tell you is it will be within this region. And when I'm making decisions, I cannot pretend that I'm only going to look at the point forecast and forget about what? Yeah, because if you do that, or if you do linear programming, or if you do ignore uncertainty and work with the averages, as sometimes people do, I would suggest that you keep your head in an oven and your feet in ice cold water, perhaps in Minneapolis when it is snowing outside, and on the average you should be comfortable. Oh, but that is how we are solving many, many problems today, where we are using deterministic techniques and we start to believe in predictions. So for me, if somebody is going to throw a die, I'm not going to predict what will come out, what the outcome will be. Gamblers do. The only claim I would make is there are 3 equally or 6 equally likely outcomes. That's all I can say. And so let's move on and talk about what we actually do. We work in the area of revenue management, which again is decision making. And here is where I would like to take you. I will try to explain the real world issues in a manner that you will be able to, should be able to relate to it. Remember here that we are defining it to be a rational and disciplined decision-making process for maximizing company-wide profits. Not maximizing things in silos, but while managing risk under current and anticipated market conditions. Now, let's start with a hotel. And I'll show you how people that love data can go wrong. People that believe data tells the whole story and the whole truth and nothing but the truth can sometimes make blunders. So imagine that you have a hotel which has 100 rooms, and the demand for this hotel, if this hotel is always full, as you see, if this hotel was always full, you will find in the data a sold out hotel. But the decisions you need to make when the demand is 150 are very different from the decisions you need to make if the demand is 1,000. We all agree that if the demand for this hotel was 1,000, we will make very different pricing decisions than if the demand was barely 150. But in both these situations, my books are going to show me that I have a sold out hotel. So how will I ever be able to forecast the true demand when that true demand data is not in your history? And if you treat the data that is in your history, I can tell you the kind of problems that you can run into. Let's take another example. In this hotel, if people are managing it, I don't care, they are managing it using systems through machine learning and deep learning, through operations research techniques, to whatever, or from their gut. No matter how they are doing it, when the demand is very, very, very strong, what will typically hotels do? Raise their prices. Despite the fact that their prices are large, they will still have a high utilization of their capacity, a high occupancy. What will hotels do when the demand is very, very weak? They will reduce the prices, and despite the fact that they have dropped their prices, the utilization may still be very poor. So if I want to understand the price sensitivity, in order to optimize the price, I need to understand the relationship between demand and price. And computer scientists and data scientists tell me, go look at the data, and the data will tell you the whole story. So I go to the hotel, and I look prices, and I plot the number of souls across those prices, and I find the larger the price, the more people buy. I wish that was the elasticity. We will all be done. And for those who still don't get it, let me put it this way to you. Get hold of a good forecaster. Forecast is a number. Until I talked about it, we were not wondering about, do we really have to understand? So let's play the stock market. Very simple. Buy low, sell high. So why are we sitting here this afternoon, and why aren't we all billionaires? Very simple. You have data scientists, you know a lot about just do a good forecast and buy low, sell high. What makes that problem more difficult or impossible is the fact that you do not know when it will be low or when it will be high. There is an ambiguity, there is an uncertainty associated with it. The same is true for almost all business problems we deal with, including pricing and revenue management. That is, we don't know with certainty what is going to happen, and therefore, when we are deciding, suddenly, if you took the volatility and then decided, okay, what is my expectation of playing the stock market, you will come to the right conclusion and say, well, unless you know inside trading or unless you want some illegal means, maybe it is not the best thing to put money in that in the hope to make a large amount of money. We cannot in the real world ignore, and this point is so important that I'll never get tired of saying it, and it should never be forgotten. So I'm going to illustrate this by means of, am I running out of time? Almost. So since I want to leave time for questions, I'll just talk about two more things. One, I want to really show you how decision changed with uncertainty. Suppose you have these bottles of water that you're going to sell, and you know that if you sold them at 100 rupees or $100, the demand will be exactly 50, not one less, not one more. It won't be 49, it won't be 48, it won't be 51, it won't be 52, it will be exactly 50 at the price of 100. And you have 150 of these bottles, and I come to you and say, you know what, I can sell as many bottles as you want. I will not cannibalize your market. I will go to no one where you are selling. I'll go and sell them in the US. I have some connections. And I will sell them for $75. How many of those bottles will you give me? 100. 50 you will keep because you make more money from them. So the forecast of demand remains the same, 50. But at the price of 50, the forecast is 50, it is 50 plus minus 10. It could be 40, it could be 60, it could be 45, it could be 55. Now, how many bottles of water will you give me to sell at 75? Well, you know that if you now kept the 50th bottle, you will only be able to sell it when the demand exceeds capacity. When the demand, that means you will be able to sell the 50th bottle if the demand was 50, 51 or more, not if it was 49, 48 or less. Assuming symmetry, it says that you will only have half a chance of selling your 50th bottle. Out of 100 days, on 50 days, you will be able to sell it, not on the other 50. So that is the point you see in the center. And then without going into the math of it, what happens is that if you look at the blue curve, that is a curve for 50 plus minus 10. And now you see where it intersects 75 is a number lower than 50. So you are now giving me more bottles to sell because you are maximizing your revenue while coping with the risk associated with that uncertainty. How do you cope with it? By allowing more to be sold at a cheaper price. Okay? As your increases, if you now increase the uncertainty from 50 plus minus 10 to 50 plus minus 2, look at the curve in black, and now the point of indifference intersection, if you look at it, is even fewer that you keep. Very interesting. And if your prices were, on the other hand, the next price I was going to sell it at was 25 instead of 75, oh, then you can do the same arithmetic, and now you will be giving me, you will be keeping more. So it depends upon whether the price, next price is below 50 or above 50. So clearly, uncertainty changes the decisions we make. Okay, I won't have time to go into more detail, so let me go back to, let me just go to the last piece where what are things that we need to remember? Think before you solve. Think globally, optimize locally. Data only tells a part of the story. I'm being kind. Sometimes data lies. And please never ever ignore uncertainty and common sense. So I said I will end with a story. So guys, listen very carefully. This story is about my favorite scientist, Einstein, who happened to be traveling with an Indian businessman on an international flight of 17 hours. And Einstein's brain was always working. He couldn't sit idle. So he proposes, how many of you have heard this story? A few of you have, okay. So indulge me, and maybe if you can course correct me if I happen to be telling not the right one, okay. So he says, well, let's play a game. The game is, you ask me a question, and if I can't answer it, I'll give you $100. I'll ask you a question. If you can't answer it, you give me $100. Well, this is not fair. You are a scientist. You know a lot. You are very intelligent. This is not the right odds. So Einstein said, okay, but all right. If I can't answer your question, I'll give you $1,000. And if you can't answer my question, you only give me $10. The guy says, done. So Einstein asked him a question about the universe or something which the guy had no clue about. He simply took out $10 and gave it to Einstein. Then it was his turn, and he says, Einstein, tell me, what is that animal that goes up the mountain on 4 legs but comes back on 3? Einstein scratched his head, couldn't figure it out. Finally, he gave up and said, okay, before we proceed, this is driving me nuts. What is it that goes up the mountain on 4 legs and comes down in 3? This Indian business guy takes another $10 and says to Einstein, here. So, never mess with revenue management, because what we call revenue management, which the airlines pioneered and which hotels are now doing, in fact, more and more people are getting into this field. This field, even today, is using mathematical techniques that belong to operations research, or we are not using game theory and we are not using machine learning. And this has got to change, because game theory and machine learning are natural fits which have not been exploited to solve this problem. And remember that whatever people may say, in India, people have been doing revenue management for a long time. In fact, my grandmother told me a story which was, and this is the last story, that you are going to go and buy something from me, oh, the sari, okay, whatever price he quotes, immediately half it. I went, okay, $100, no, 50. 50? No, 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 25. Finally, the man got so irritated that he said, okay, come on, hell with you, just take it free. No, I want two of them. India is far ahead when it comes to revenue management. Thank you for your attention.